Good morning, ladies and gentlemen. So we're just solving this problem here. It's draw the shearing force and bending moment diagrams for the beam and loading shown below and determine the max absolute value of the shearing force and of the bending moment. So that's our diagram here, with the only things missing, which are the external force members. So those are the ones we will calculate first. Now, if you follow me to 2 here, we are solving for the external force members. Quite simple if you've done statics before. If you want to solve for B, we do a sum of moments at A, and that's just the distributed load multiplied by 2.4 and then multiplied by the center where that load is acting. Not forgetting to add since we defined the moment to be positive in that direction, we're adding 15 and then we're taking away 25 because there's a moment at point A, so that's taking 25 away. And then because FB is working into the negative direction, we're just doing negative FB times 3.6. And that will give us FB of positive 29.222 kilonewtons. Next, we will do the sum of forces in the y direction, having our direction positive to be up. So that will be just the distributed load. It's a negative direction multiplied by 2.4 plus FA, which we currently do not know, and then plus FB, which we calculated to be 29.222. And then we find that FA equals to 66.78 kilonewtons. Next, we will calculate the shearing forces, and I will go from left to right. You can go from right to left, depending on what you fancy. But anyway, the shearing force at A, we cut a section just past FA, just slightly past. Of course, it's not to scale. And then we will have the force FA, which is 66.78 in the positive direction, and then the shearing force will act in the opposite direction to that force, so downwards. And then when we do the sum of forces in the FY, the shearing force at A will be 66.78 kilonewtons positive. Next, we will calculate the shearing force FC. And shearing force FC will be cut just smidgen past C, and it will be 66.78, which is that force for FA. Then we'll have that distributed load, which will act in the negative direction, and then multiply by the distance 2.4, and then minus shearing force FC, all equal to 0. And then shearing force FC will equal to negative 29.22 kilonewtons. Then, since we calculate all the shearing forces and we have a distributed load here, you will see later, or in this image, we have the shearing force diagram. And the distributed load, it will cross the axes. So we need to figure out, at 4, we need to find the x value. And all we're doing here is we're balancing triangles. So we have the shearing force, FA, which is we found to be 66.78. We divide that by its distance, x, which we do not know. And then we equate that to the large triangle, which is 66.78 plus 29.22. And we divide it by the whole distance, which is identified here to be 2.4. And you'll find that x will equal to 1.67. Now, next we will find all the moments using the shearing forces and the distances known, because moments are just areas in the shearing force graph. And this is how it's done. So moment A to D will be the force, the shearing force A, multiplied by the distance x, divided by 2 because it's a triangle. And then we cannot forget to minus the negative moment here from that overall value. And then that will be equal to 30.76. Now, if we have a look at this moment MAD, and we need to draw this on the moment diagram, we will start at negative 25 because of that initial 25 moment in the negative direction. And then we will draw a curved line to hit 30.76, and that will align perfectly with where that distributed load intersects the x-axis on the shear force diagram. Next, we will do the moments D to C, which will be similarly shearing force at C. It's a negative multiplied by 2.4, which is that distance here, minus our x, and divided by 2 because it's a small triangle, and that is equal to negative 10.66. Now, on the moment diagram, we will draw this as a curved line, and we will draw it, and the value for that will be, where that curved line will stop, will be 30.76 minus 10.66. So that point here will be approximately 20. So, and then we'll proceed from there. We'll stop at that point. Next point will be MCB. MCB is the, because there's no other forces acting at C, it's just a straight line shearing force distribution until the final value B. So we will go negative 29.22 multiplied by 1.2. It's just a rectangle, so we don't need to divide it by anything. And that will give us a negative 35.064. And then we will just draw a straight line from there to the end where the lines with B, point B. However, we're not done because we still need to account for that moment at 15. So therefore, we will add 15, and you will find that this moment diagram will conveniently end on the axis, as it should. And then to completely finish off the question asks for max absolute value of the shearing force and of the bending moment. Those are M max, that's our 30.76. The reason it's 30.76, not 35.064, is because I've separated this component and this component in order to show in an easier way how this is drawn. In reality, this would be negative 20. And then the V max, that's the same as shearing force at A. That's the largest value, which is 66.78. Thank you very much.